So lecture on process control, manufacturing or production and automation on 17th of November. Today's lecture is dedicated to some intelligent techniques for modeling and control. The first one is related with modeling the neurons in our human system by artificial neural networks and how they are comprised and trained and implemented for different purposes related to modeling and control. The next intelligent technique related with laboratory 3 will be based on decision making in a human way using words based on fuzzy logic. So starting with artificial intelligence, it models the functioning of our brain. Artificial intelligence is a knowledge-based system based on expert knowledge that processes symbols described in a semantic way and rules to model non-logical and subconscious human behavior, which artificial neural networks can model this, while the knowledge-based systems, previous level expert system, they cannot manage with the big information from numerous sensors, and they cannot tolerate non-logical subconscious data. So artificial neural network is a step further in the development of artificial intelligence. They are structural and functional analogy on micro level with the human brain. So they imitate the functioning of the biological neurons that comprise a communication system. So the artificial neural networks related with learning knowledge, storing in neuron connections this knowledge and distributing it along the different neuron paths. It is a dynamic approach for modeling and solving problems like classification, function approximation, and they are tolerant to imprecision and can process and compactly present results from training. So the definition of the artificial neural network is a parallel processing, distributed processing, or information system based on simple processing elements that accumulate information and transmit it through to other neurons, or mathematical abstraction of human cognition and neural biology. So developing this artificial neural network, we return back to the original neurons and have some models for their functioning. The artificial neuron imitates the biological prototype. The neural cell has soma, body, nucleus, axons, very long. They turn processed inputs into outputs, so they are used to obtain the outputs of the processing. The processing is in the neuron body, in soma. They are very small extensions. They accept inputs from other neural cells. They are called dendrites. The connection between dendrites from one to the next neuron cell are these dots called synapses. So this is the connection where the presynaptic signal is transferred into chemical signal and backwards. So all aggregated irritating signals from environment through sensors or via other neighboring neurons, when they exceed a given threshold, the neuron generates output. It is action potential, so it fires and sends along the axon, the big extensions, pulse to adjacent neurons or to our motive muscles. This output controls muscles so that we can give response in the form of some action, some words, talking, or some other final reaction. The artificial neuron. Some saw irritations, P1, PR are all input signals. They are weighted with the tuning parameter, the weights, and their input to the nonlinear transformation from the body of the nuclear cell may be using bias. This bias often is connected as if we have input equal to 1 and the bias is equal to initial weighting function. So the idea is that weighting functions and biases are tunable parameters in order for a given combination of inputs to obtain desired output. So to train our artificial neural network in a way to perform some operations the real biological network performs. So to take some intelligent properties from the biological prototype. One neuron, this one, has inputs, activation function, but it has not very great power in modeling or in performing given operation. We need network of such neurons. The network is trying to compete the human brain with the human brain has a lot of neuron cells and more connections and still is superior to any existing machine because it's faster, can perform sophisticated parallel intelligent activities like recognition, motor control, and has desired feature tolerance to mistake, accommodation to changing environment via learning, so it adapts its behavior, processing of improbable contradictory data, or feeling missing data, successfully feeling the missing data. And still it's very compact in size and consumes smaller amount of energy. The unique neuron property is capability for receiving, processing, and transmission of electrochemical pulses over the neural paths, which constitutes a communication system. So this is related with the information that is passed from neuron to neuron till a final action is taken. So we'll speak about three basic components or characteristics. A neural network has architecture. Usually multi-layer network has a number of layers and number of neurons in each layer, and connections between layers. There are other architectures besides this layer structure, like stars um, and other arrangement of neurons. Activation function gives the rule for neurons to produce output from the weighted sum of outputs, which is biased. The learning algorithm is how from inputs we obtain desired outputs by changing the weights and the biases of all neurons. Several neurons in a layer or multiple layers with nonlinear activation functions in the hidden layer have much greater computational power. If we use a two-layer network or three-layer network and sigmoidal neurons in the hidden layer but linear activation function in the output layer, we can produce a general function approximator. Any nonlinear function with finite number of first order interruptions, where this is the place where derivative doesn't exist, first order derivative doesn't exist. So they can be approximated by a multi-layer, 2 or 3 at the most layered network. So the examples of architecture: single layer FEDU. So inputs one layer and the number of neurons of the outputs and the number of inputs are determined by the problem we solve. The power of this network is limited. Multi-layer, hidden layer. Here neurons are subjected to design. The number of neurons, the activation function is nonlinear, usually sigmoidal. I'll show you later. So inputs and outputs determine the problem. They are fixed by the problem, but the hidden layer is free to design. This two-layered network has a great computational power for approximating any nonlinearity, so it is most often used in solving problems from control and modeling for control. There are other types which are called recurrent neural networks that contain dynamic properties because the next moment, the training contains inputs which are taken from previous moment output. Z to -1 is a delayed by one sample period signal. So we produce the signal from previous moment and passes as input in the current moment. So the recurrent networks, because they have memory, they memorize this previous output to pass it in the next time instant. This memory for one pass value makes possible to represent or to model dynamic systems. Dynamic system, they, for instance, time lag element that is described by first order differential equation. The first order derivative is often substituted by finite difference, current measurement minus previous measurement. So the time lag can be modeled by such a recurrent network. Some networks may have for inputs not only the previous output but previous two previous moments input or 3 previous moments. So we have different high order dynamic element that can be represented by the recurrent network. The activation functions can be thresholds. Here you see the bias. It's not along the change between plus minus 1 takes place at abscissa equal to minus b, not to 0. So it's not symmetrical with respect to the origin of the coordinate system. And asterisk, this is the accumulated weighted inputs. So the sum of weighted inputs. So the analytical expression for the output depends on the input. So you see the input is the real input plus the bias, and linear with limits are used to model adaptive linear filters, while the first one was for the initial neural networks, where this neural network was limited, couldn't perform some operations needed for computing, substituting computer. So perceptrons are called neural networks that use such activation functions, and they are mainly applied in solving classification problems. So the input data is first divided into classes called clusters, and each class has specific properties, and we arrange them in some classification. The last two are differentiable monotonic sigmoidal functions. The first is related with logistic sigmoid. It's bounded between 0 and 1. This is the output. So hyperbolic tangent is another sigmoidal tangent sigmoidal function bounded between with output bounded between -1 plus 1. That's why to eliminate these bounds, sigmoidal functions are used for transformation in the neurons from the hidden layer and to make more powerful the network. But to enlarge these boundaries, we use linear linear activation function at the output layer. So we expand the result to -infinity plus infinity. Or if the outer layer has also sigmoidal function, one of these two, we have to normalize signals for training network input and the corresponding desired output for this input called also target. So the training is unsupervised. We do not know what is the result using the so-called Hebbian rule. We apply different combinations of input signals, and initially the weights are randomly initiated, random values for the weights. At the first epoch, when all combinations one after the other are applied, we use the outputs of two adjacent connected neurons. One is called source, the other receiver. If their outputs are great, the update of this pathway connecting these two neurons is increased. There is always a learning rate to speed up learning process. So the next the next moment, the weights use the previous moment weights updated with this delta W. Finally, when all training finishes, we have a similar relationship between outputs as this is observed in the inputs. So this is a good task to classify the inputs. The neural networks require input data only for inputs. The task is clustering and classification. Often self-organizing maps are using this type of training. The second is using a teacher, which means for desired combination P1, we have a target. For a given combination at the input, we have desired output. Then another combination, another desired. So this is the training set that is applied for training. Initially we have random values for the weights and the biases. Apply the first training set, training couple. The output is arbitrary, probably far from the target, and error appears, it is memorized. Then we go to the next couple. Till all couples pass, we accumulate all errors and obtain the cost function, which can be sum of all squared errors to eliminate the sign, whether it's positive or negative error, or mean squared error. So the sum is divided by the number Q of these training couples. This cost function finally is used to update the weights and the biases. With this, an epoch finishes. Then with the new updated weights and biases, we repeat another cycle called epoch. Again, applying the couples one after one, obtaining output, error, then new couple, new error, till all couples are used. So we compute the cost function based on the sum of all errors and update. We do this many times, so it's iterative process, trying to minimize the cost function. So it is an optimization problem. The cost function, when minimized to a given value, the value which we put for the cost function, the minimal value, it is given by the designer, by the operator. So it is subjective. Else, we have to bound or limit the number of epochs. So one of the two satisfied, this is the end condition. So I told this is a minimization of some cost functions, optimization problem. The unknown parameters are these biases and weighting coefficients. Their number should be smaller or equal to the number of equations, like in mathematics. For two unknown variables, you need two equations. Here we cannot count because the models are very complicated, but we have to ensure a lot of training data. Still, the greatest advantage of the neural network is that we do not use much training data to be able to approximate a given relationship through this experimental simulation obtained data. So we have some observations on the plant or on the controller. We have designed the controller. It is on computer. We can investigate applying inputs and recording the corresponding outputs. So we have this data from experiments or from simulation, and we try to reproduce the functioning of the controller or the complicated plant by training its model. The model has a very small cost function, so the error in all these points is very small. But what happens in between points when we have some other combination of inputs not included in the training? So we have to check for such signals, input signals, and if the output is similar to the neighbor outputs for neighbor input signals, this is a good generalization. In mathematics, it's called interpolation. So we have to check whether our artificial neural network operates correctly with any signals in the given range. Usually the training input couples are taken from experiments or simulation, are divided into a part that is used for training, and the rest of it, 1/3 usually, used for tests for generalization. If generalization is perfect, we can use this model and trust it. But if some peak appears at the output, quite different output from the adjacent outputs obtained for adjacent inputs, this means that we have to retrain the model. In retraining without any change, we just start from another initial point, initial values, random values for the weights and the biases. So from this other value, we have to train totally our network. Here I explain that the training of multi-layer network is based on backpropagation method. Simply, if we have one neuron with one weight to be the unknown parameter and cost function, a square error, we obtain the updated weight when we apply the all training couples, obtain the cost function and its derivative with respect to the tuning parameter weight and the weight coefficient. So epsilon, the derivative d epsilon dw uses the chain rule because it is implicit relationship. W is not exactly present in the cost function. It is present not even in the error, but in the output, not exactly in the output, but it is present in the input to the neuron, which is WP, one input, one weighting coefficient, and one output of this neuron is demonstrating this. So we need the epsilon dE. This expression results in E. This is called the delta function. It is function of error. Then dE, the output of our neural network. Then the output of the neural multiplied by the derivative, the output over the output is actually the activation function over the input. The input is WP plus bias. Eventually here bias is not explained. And finally the input over W, which is equal to P. So we have P and delta, and this is how the update in this simple case is done using the simple delta rule, which is derived by Widrow and Hoff on the base of gradient descent, because we obtain the derivative of cost function with respect to tuning parameter. This derivative taken with minus results in this expression. Because it is known from mathematics that if we change a parameter opposite to derivative or gradient, this is the fastest way to reach the minimum of the cost function, because this gradient is the derivative of the cost function with respect to W, the tuning parameter, the unknown variable. So when we have multi-layer network, this rule is applied from the last layer. So the first thing is that we pass through all layers to obtain the output. Then the output is compared with the target. We obtain the error, and this error is used to compute the update at the last output layer. Then this is distributed to the previous layer to compute or update or compute delta W in the previous layer. So we start from second layer, it continue to first layer, updating weights, and in a similar way biases. The update is again based on the cost function and the gradient related with the derivatives of the cost function with all weighting coefficients. So it is complicated derivative. This is actually the so-called gradient. So this update is related with the error, but it's not only error like here. It is related with the differentiation of the output with respect to W. So this is related with the output is the activation function. A2 is equal to F2. And after that, differentiation with respect to N, which is giving us this delta function. The delta function depends on these components, error, derivative of function, and also input. So input to this layer, input signals to this layer. So look here for delta function, the first in one layer network, P is the input and delta function is Z. For two layer networks, we have some generalized delta function that depends on this expression. And we change the weight by updating with delta W2. So this delta W2 is based on learning rate on this defined delta and output to this layer. It is not P. P is the output to the whole network. Now layer after layer, each layer has as the input the output of the previous layer. So we have here input to second layer, the output of first layer. So when we have all these deltas obtained and we can update the weights, you use these deltas here. They are multiplied by the new weights and summed to obtain the delta vector for the hidden layer. So this is derivative of the activation function. It's one and the same in all neurons in this hidden layer, and the sum of all deltas from previous layer computed. And this is what is used as delta vector for updating the weights. So the new weight is the previous time updated by a learning rate, the new delta, and the input to this layer, which is the input to the neural network. So graphically, it is explained here. The signal flows through all layers to finally obtain the output. When the output is compared with the target, desired output, the error is obtained, and then we compute the delta vectors used to update weights of last layer. When we have all delta vectors, we sum them. So you see, we need derivatives of activation functions. So we use some sigmoidal functions or linear functions. So we obtain the delta vector for update of weights in previous layer, and if there are more layers, we return to the final layer closest to the inputs into the neural network. So this is error flow, opposite to signal flow. That explains the name backpropagation of error training algorithm. And the phases we initialize by random numbers, weights, and biases. Apply some method for computation of learning rate, set 0 for the number of epochs, define stop condition reaching some minimal value for the cost function, or reaching the maximal number of epochs, of cycles, of iterations. The first phase is computing the file layer after layer, the final layer output, checking if this output, so this output is related with computing the error in check phase and computing of cost function, some squared error, for instance. Then checking if this is minimum, or checking if this is the last epoch to go out of the cycle. So else, if this is not satisfied, the end condition is not satisfied, then we continue with calculating of all delta functions from outer layer to the first layer. And then the learning phase is updating the new weights, obtaining new weight matrices and biases. So the weight matrix and the bias vectors. And then we return to presentation phase, feed forward, passing with the new weights all training couples to obtain and the outputs for each. And further, so when we go out from this cycle in the checking phase, because either the number of epochs has reached its maximal number, or the cost function became very small, then we use this the rest of the data for cross-validation and for test for generalization. So for intermediate data, which is not used in training, we try to find whether we have output which corresponds or is smooth continuation of the output between two outputs for which we have training. So this is important. So the neural network can, based on gradient descent, has some strengths. It's a very great application and representation and generalization, but they are not insured, guaranteed, and the models are black box models. We do not know the role of neurons and how to change number of neurons in hidden layer, how many hidden layers. Each time we introduce some change in the model to improve or to be able to ensure both good modeling and good generalization, then we have to restart training from the beginning. So it is a non-incremental deficiency, and some parameters are based on our subjective selection or choice. Improvements are possible to consider that this relationship, that the hidden layer number of neurons is related with the training set, the number of inputs, and the number of neurons at the output layer. This is giving a relationship between the number of now unknown parameters and the number of training couples, the experimental data for which we have to train. Because if we have many neurons with many unknown weights and the training set size is small, so a few couples, it's quite probable that we wouldn't have reached good accuracy or generalization. If we cannot exactly measure this because the model is huge, we just try to change the model if we do not have good results from training by increasing the training couples, the number of points taken from experiments and simulations which are used in training. So let's apply this to modeling problems: classification, identification, optimization, noise nonlinearity, compensation or cancellation, prediction, adaptive nonlinear control, complex processes which have variable or time variable parameters. So these are called complex processes with parameters that change with time. Advantages for such models are that they can present any nonlinearity, which is a complex logic function or control algorithm, usually nonlinear. There is a standard for configuration and training of artificial neural networks used in different microchips and PLCs. Siemens has NeuroSim additional software, which applied with intelligent camera. The camera supplies input training data. NeuroSim trains designed by us a neural network to substitute, for instance, for classification, the quality of tiles. So the camera takes expression that is turned into frequency domain graphs, the magnitudes, and they combine different factors like shape, good rectangular shape, good color, uniform color, weight. So the plates should be thin, so dimensions and so on, in representing into the frequency domain as a magnitude characteristics taken from camera, and this magnitude characteristic for different training couples. So first class tiles should have a magnitude characteristic of one type, second class different type. So after training with these training couples that give us the quality of the tiles, we can obtain this we can use this model for unknown quality tile. It will result in some characteristic, gain characteristic, frequency characteristic, or magnitude characteristic, which to a certain extent, to the most, the greatest extent, coincides with class 2, for instance, the graph of, for class 2. So the network will give us exactly a class 2 belonging to the current tile, or class 3, so it makes this comparison because the network is already trained and can say which tile to which class can be applied. So this is related with Siemens. There are other neural networks connected to specific controllers. So I have a lot of examples, most of which I suggest that you read. Here we have boiler. We use the produced pressure, steam with a pressure P by changing the flow rate of fuel. The transfer function, pressure over flow rate, is a second order time lag with variable gain that depends on the number of consumers of this steam. The more consumers, the greater the drop of pressure. So the more steam has to be produced. So we have this dependence consumption for fuel, tons per hour, and the gain function of consumption. Also, we'll have the steady state characteristic, which gives the gain, but you see the gain and there is a bias, both dependent on the consumption. The idea is to abolish this relationship with the number of consumption and consumers. So we want a neural network added to the plant as a trained block with a gain with mirror relationship to this one, so that the product of the neural network gain and the gain of the plant to give 1. So we'll eliminate dependence on consumers. The block diagram, this is variable gain of the plant. This is the dynamic part. For S equal to 0, we have the steady state. The steady state is 1. So this signal and these signals, the two signals are steady state pressure. And the neural network is trained For the same PI controller, we have possible values for the output voltage in this range, -10 plus 10. D has discrete values taken from experiments. They are 8, 10, 12, so we make all possible combinations from D and U values and normalize them with respect to maximal possible value. So we divide by their maximum to have inputs in the range between 0 and 1 and train a network for desired output. This desired output is related with gain of neural network multiplied by this gain from the steady state equation. This means that the output of the neural network will pass through this gain and in steady state has some initial value bias, and this will result steady state pressure is equal to voltage pressure of controller. Voltage pressure from controller is equal to steady state pressure because in steady state this block is 1. So we take this derived steady state linear equation. This is obtained experimentally. So we have lines with different slope given by the gain and different deflection initial value. Again, nonlinear function. So for each D, we can compute PO and KO, and we can have PO, KO for the given D, and in combination with U, we can compute the target. For this U and this D, the target, the output of neural network should be this. And it is again normalized between 0 and 1. The linearized system doesn't depend on this main disturbance, and we have linearized gain equal to 1 of the plant and second order time lag for the dynamic behavior in the transfer function of our plant. So after training, we have weights in first layer and biases and weights in second layer and biases. So we have 1, 2, 3, 4, 5, 6, 7 weighting coefficients, and so 7 inputs. So the hidden layer, first layer, has 7 neurons. The output layer has only 1 neuron. This is the target for the corrective voltage from the controller. So this is called controlled surface. The control surface gives the relationship output of neural network as function of the two inputs. The two inputs are not normalized, only the output is normalized because here we use sigmoidal, logistic sigmoidal from 0 to 1 nonlinear activation function, and the output is limited between 0 and 1. Here we have different adaptive controllers. You can read them by yourself, and predictive controller for a very slow process, which is modeled by a very complicated model. This is degradation, biodegradation of organic wastes by using two stages, using pseudogenic bacteria with concentration X1 that is fed with substrate. Part of this initial organic waste is turned into substrate for the two bacteria. The first substrate for acidogenic bacteria, the second S2 substrate for the methanogenic bacteria. This process has input the dilution rate. This is the quantity of pure water added to the organic waste. This is a cattle waste in water. So it is diluted to a certain extent to give proper substrate for the two types of bacteria. And the dilution should not exceed 0.3 and should not be, it is between 0 and 0.3, which means above 0.3 the dilution of organic waste, the food for the bacteria is greater and the bacteria may die. So we have coefficients which are dependent on the variables X and S. The disturbance is the different organic waste concentration, SOI. This is the initial organics, which is decomposed into food for one type of bacteria, for other type, and the methanogenic bacteria emit biogas when the biogas flow rate Q is very high. This means we have most of the organic waste is digested. So the final algebraic equation is a measure for the degree of organic digestion, of purification of water from cattle waste. Different characteristics show that we have some optimal relationship between input control D and output degree of purification related with Q, with biogas. The biogas serves as an alternative fuel because it contains 80% methane. So the step responses differ. For one and the same step change, we have different change by magnitude, which says that the plant is non-linear. And this is dependence on the disturbance. So greater disturbance, more time is necessary this initial organic waste to be reduced to 0. So complicated plant, we model it through this model, but the model is not so precise, so we apply different changes of input D, of disturbance, and of parameters. And the data collected is normalized, the input, and the output is the next day or the next in the range of data output of the plant, Q. So the target is shifted Q to future values. Here we take 1 day in future, the value observed in simulations for all possible parameter changes, disturbance, and input dilution rate changes. So the more data that reflects all possible situations, the better the model, because it will react in a proper way to all possible behaviors of our plant. So that's why we need rich in magnitudes and amplitudes data that covers all operation points, all the range of operation of the plant. So we predict by training the neural network with target predicted value for biogas production. based on current values, previous day values, because the plant is very inertial. We speak the time, measure the time in days, and we have a good predictor, which in the feedback predicts what will be the behavior so that the controller changes properly the dilution rate, sending this to the plant for opening more or less the pipe that supplies this tank, the bioreactor, with the fresh water. The flow rate of the fresh water considers the delay of the plant, so it is up to date using this predictor in the feedback. The predictor is artificial neural network. So up to here, I'll close this lecture, stopping our lecture on process control, manufacturing or production automation on 17th of November, part 2. Now, another intelligent technique related with the way we take decisions like humans is fuzzy logic. We'll first learn something about the theory and then how to apply to obtain different models and controllers. Fuzzy sets are defined as a couple for each element on the axis. So axis is the measurements in physical units in a given range. So U is the variable that we measure. So for each value from the axis, we have belonging to this fuzzy set with different degree. So several values are accepted to have the same common property to belong to this class, but they have this common property with different degree estimated by experts. Imagine this is temperature between minus 20 plus 40, and in this range, most people say this temperature is good for the room if we control the microclimate in a room. So, but you have 100 experts and you ask them, what about minus 20, then minus 15, minus 10, minus 5? And each time you ask for a given temperature, the experts say, yes, it's good temperature for the room. But minus 20, no one says it's good from these 100 experts. For minus 15, there are 3 people. On increasing the temperature, the number of experts that agree say, okay, in the middle where the peak of this triangle is, all experts say this temperature B is good. So 1 means 100% of experts agree. So this is a fuzzy set which describes the opinion of experts, the agreement of experts upon whether these values of U with what degree belong to fuzzy set labeled as good temperature. So fuzzy sets are ordered couple, value, degree of membership. And if experts are asked, we wouldn't obtain exactly triangle, but we can approximate their opinion agreement with different shapes. So this is how we represent fuzzy set graphically through the shape of the membership function, which is typical for approximating the opinion of experts. Typical are triangle or lambda type, trapezoidal, Gaussian, bell type, and singleton. The last one, singleton, means that there is only one element that belongs to this fuzzy set with degree 1. Mu is the degree of membership function, so this is the degree of belonging of the corresponding element to this fuzzy set. Fuzzy set is more generalized representation of ordinary sets. So if A is ordinary number, we make it singleton. So it is a fuzzy set in the shape of singleton in order to have operations over fuzzy sets. So if we want a number to manipulate a given fuzzy set, we transfer this number into the more general form fuzzy set with the shape of singleton. So there are other more complicated combinations of this. These are the most important. The fuzzy logic toolbox in Siemens controller. It is additional software to program fuzzy logic controllers. And it uses for description of the inputs to the controller fuzzy sets in the shape of triangles, where if B is equal to C, we have the case of triangle. So trapezoidal is the used one, but in for B equal to C, we obtain as a private case triangle. The output membership functions are singletons, and we'll see later why. So these fuzzy sets give us the degree of belonging of each value to this shape. So to this fuzzy set. So the degree of belonging as function of U is the graphical representation of the fuzzy set by its membership function, the graph of the membership function. So it's important not if this element belongs or not, or to what degree it belongs. If U is greater than C and smaller than A, the degree of belonging is considered 0. Then some operations over sets. The operations over fuzzy sets are operations over their membership functions. This is union, taking the cover, the maximum membership function of the union. Union is denoted as C. It is also fuzzy set with membership function, the cover of this, or the maximum of the membership functions of the fuzzy sets A and B. Intersection or conjunction is related with product or AND operation. This means the two contacts are in series, and in order to have current in the circuit, they both should be closed. Union is alternative. It is operated, disjunction. So the contacts are in parallel. They are feeding a circuit. So either one or the second, either the first or the second, or both should be closed in order to allow feeding of the circuit and current in the circuit. So OR corresponds to fuzzy logic summing and corresponds to fuzzy logic multiplication. Or is alternative and is simultaneous closing of two contacts. So a complement is the not operator. It is in the ordinary logic called negation. But here, the complements, so if A is the fuzzy set with membership function this in thin line, the thick line complements the thin to 1. So the negation is actually complement to 1. These three operators build any other logical system. So all other operations can be expressed through these three, which are called basic system of logic operations. So the logic operations further can be algebraic sum and algebraic product. These are very important because algebraic sum is an operator which can be used for union. An algebraic product is another way to solve a conjunction. So the conjunction and prod are equivalent on the basis of the basic laws for ordinary sets operations. So the ordinary logic for related with ordinary sets uses some basic rules, and these basic rules are fulfilled for two or more operators for conjunction and for more operators for union. Two of them are max and algebraic sum for union and min, the minimum of the membership functions which are intersected. So the minimum or the product, because each of these operator satisfies the basic laws on which we build the ordinary logic. They are common for the logic in over fuzzy sets and over ordinary sets. So we can also have 2 power greater than 1, which is called reduction of fuzziness, because the basis, the area for which non-zero membership functions have this variable u is smaller. So this is decrease of fuzziness when we put to power 2 the fuzzy set A. But if the power is smaller than 1, we have dilution of this fuzzy set, increasing of fuzziness with the bold line. So the basis is increased, so more values for u belong to this fuzzy set, so the fuzziness is increased. And these are the basic operations we need further. Fuzzy logic is used for modeling and control when we have variables which cannot be precisely measured, or their measurement are mixed with other factors, many factors that influence the variable. So this variable even cannot be measured, should be estimated like quality by experts. So the variables do not have exact values, numerical values. They have approximate values that this has more quality nature than quantitative nature. or if there are not simple applicable mathematical models, to use them to design a controller. So the model of the plant is complicated, or the objective for the control is vague, overshoot 20%. Why not 15? Why not 22? So there's fuzziness in the objectives to reach desired performance of the control system. Or we have enough operator experience and knowledge to structure in fuzzy logic controller. So the fuzzy logic controller doesn't use mathematical models in the classical sense, but it uses a lot of knowledge based on experienced operator who controls manually the process. So it's a protocol which contains rules. If something happens, or measurement is this, or the measurement belongs to this area, or the expert sees this, then the control action is that. So the controller, based on fuzzy logic, models experienced operator actions. We have to represent measurement by degree of belonging to a certain state. And for this degree of belonging to a certain state of the input variables, we derive the degree of belonging of the control action to a given other state. Its state is represented by a label, name, this is a linguistic term, and a fuzzy set it labels. So the fuzzy sets overlap. There's always one in the middle, which is the norm, the desired state. And experts assign how many states are necessary, and their overlapping is at the degree 0.5 of membership function, which ensures orthogonality. This means each measured temperature in this example belongs to several or to all these defined states with different degree. For instance, if we take 70 degrees, 70 degrees has membership function for belonging to low. A1 is the general for low. Low is a label related to temperature. So 70 degrees cannot cross the trapezoidal membership function for low. So the degree of belonging to low, mu1, is equal to 0. The degree of belonging to middle, it crosses this triangle in the middle, called middle, labeled middle, at the membership function, which is the ordinate of this cross point. The ordinate is 0.4, for instance, or 0.3 or 35, so 0.35, for instance. The belonging to high is with degree that complements 0.35 to 1. That is due to orthogonality. So mu3 is equal to 0.65. So for each value in this physical area for the linguistic variable is the name of our variable. It takes values in this universe of discourse. here between 0 and 100. So each linguistic variable shows that temperature will be approximately measured. It's better to know how far from 100 norm it is from this 50 degrees, which mark the 100 norm, percent norm. So this variable u is called linguistic because we wouldn't speak about its specific values, but it has name x, in our case u, term set, number of label. So the term set contains the labels of the states, the 3 states. So term set, these are labels or terms, the names of the sets. So low, middle plus high, they all make the term set. This is the universe of this course, all values between 0 and 100, semantic and syntaxis and semantic sense rules related with the sense, the meaning. So this means that the name low, middle, and high, they can be related to temperature. Low will correspond or will label a fuzzy set defined for low temperatures in the universe of this course. Middle to the desired temperature. Desired, which means these are the proper temperature for good process inside installation. For good climate in a room, for instance, or for preparing good tea, and so on. Temperature, liquid for good tea. So the sense, the semantic rules associate the label with the position of the fuzzy set. So there should be a meaning between two. You cannot place at low temperature the fuzzy set and label it high. So this is the formalization called fuzzification of each variable at the input and the output of the controller. It should be represented by linguistic variable with different states labeled with terms from the term set to cover the universe of this course and to obey the allocation of each fuzzy set. The name of the label should correspond to the allocation, and they should intersect to ensure orthogonality. The fuzzification is to each measured value, which may contain expert knowledge, it may contain measurement and interference of noise and so on. Each value for u is converted into degree of belonging to all fuzzy sets or to all sets. This way we know that the current measurement 70 degrees or estimation 70 degrees belongs dominantly to high temperature, less to middle, and very far from low. So we are on the right of the perfect norm. So we cannot trust exactly the value 70, but we want to move this by the help of controller to the exact norm. So fuzzy set is ordered couple, membership function, an element that belongs to this fuzzy set. Fuzzification is the process of turning of a measurement or estimation to degree of belonging to all defined fuzzy sets. This is done, you are the expert and you have to know how many states you need, number of terms. Also, you have to partition correctly the input or output space. Usually grid partition is used, so we assign these fuzzy states that correspond to a grid relating input and output. And normal element, this is the desired, the reference, the desired or the mean value, the type of membership you as expert has to decide a triangle, trapezoidal, Gaussian, and so on. In the memory of the fuzzy logic controllers, it's better to have simple like trapezoidal shape, which can be converted into triangle by proper parameters. These membership functions besides the type have parameters. They have to overlap to cover the whole range. The allocation should be covered. Each membership function intersects the neighbor one, ensuring orthogonality, and they are ordered according to their terms: low, middle, high, first, second, third. So the linguistic variable is the most abstract. It is described by states labeled with low, middle, and high. After that, through membership functions, the states are connected with the universe of discourse, which is the numerical values for the linguistic variable. So, computing on the lowest bottom level with numbers, we can manipulate words. So, fuzzy logic is called also computation with words. So, you define words and how they are related with the numerical values, and compute words applying rules on the numerical values. The interconnection between input and output to a modeled plant or a controller, modeled operations, actions. This is the controller. Requires that we connect obtain desired output for the given input. This is done through fuzzy rules. They have if part and then consequent part. The antecedent, the if part, gives some condition called proposition, predicate, premise, prerequisite. The then part is the result, the action, the conclusion. We have simple if clauses, statements. If X is A, then output variable Y is B. Behind X and Y, we have specific estimation, so a number, or evaluation, or measurement. So we have a number which is compared with state labeled by A. And the conclusion that has to be derived will be a fuzzy set labeled by B, which is qualified to the degree of fulfillment of the condition. So if X is crosses the fuzzy set labeled A at degree 0.3, then B will be cut to level 0.3. So if B is a fuzzy set trapezoidal shape, you have to cut it and take a small part of it with uh, height equal to degree of fulfillment of condition 0.3. It's simple premise, but if we have simultaneous fulfillment of two or more subconditions connected by and or, this means we have degree of belonging of x1 to AG, degree of belonging of second input x2 to BM, sum of its states, which is a fuzzy set. The two degrees are compared using and or operation, and taking the minimum or for taking the maximum. This is a composite multiple antecedent premise or condition. For instance, in a PI controller, you need error, PD controller, error and derivative of error. If error is small, you know now where this fuzzy set is and what type is. It is located for small values for error, and possibly it's triangle or trapezoidal. And derivative of error is high. High is on the opposite end of the universe of this course. So it is the universe of the course for error is 1, for derivative of error is another. Then output should be what? The minimum of the 2 degrees of oscillation, 2 degrees of fulfillment of the two subconditions. The smaller of these 2 degrees in end connective will qualify the fuzzy set corresponding to Cn. So output will be fuzzy conclusion. It will be a fuzzy set, but not the original, but it will be cut to the level of fulfillment of this composite condition. If instead of fuzzy sets, the conclusion contains deterministic function of the inputs, for instance, linear or constant or second order, we have Sugeno models. If this deterministic function is linear model, dynamic model in state space, we have the Kagi-Sugeno-Kang model, and it is computed. The output is computed, even if it contains differential equations. We solve this model, and the output is qualified by taking part of it. So if we have degree of fulfillment of the condition 0.2, the output is computed to be 0.6. So this 0.6 is multiplied by 0.2, or it's taken with degree if we apply product for AND operation. If we take the minimum, we just say this 0.6 is a singleton with height not 1, but 0.2. That's why I paid attention to singletons. These are values which belong with the degree 1 to this fuzzy set. This is on the value A. So A is exactly this fuzzy set. But here we have a value which allows to put a singleton to this value, but it will be with height qualified, not 1, the degree of belonging of this value to the fuzzy set singleton, but it will be with value 0, degree of 0.2. What this means, the height of this singleton will be 0.2, not the maximum 1, but 0.2. It will be qualified. So one if-then rule relates input with the corresponding to it output in the way the expert has defined which variable is input, which variable is output, what states each variable has, how they are allocated over the numerical axis, numerical values for the variable on the axis. So it is relationship also that contains cause-result relationship. First, input appears, then output is computed. And this is related with one state to be able to have output for each combination of inputs. So we need more rules. The rule base contains all combinations for the input states. When we have one input and n states, we have n rules. If we have two inputs, the combinations, if the first has 3 states and the second has 5 sets, all combinations are 15, so we need 15 rules with a proper output. The output aims, if it is a controller, to, in the next time moment, to move these measured values for x1 and x2 towards their norm terms to enter the desired value to reference and to mean value. So the desired term should be reached by proper action on part of the controller. So we have two types of models, as you can see, depending on the conclusion, whether the conclusion contains fuzzy sets or deterministic function. If the deterministic function is constant, you say for this situation for temperature x1 and pressure x2, the fuel should be 30% constant opening of the valve. So 30% is a constant. So we have deterministic function of zero type, and Sugeno is called zero type model. The linear is first order Sugeno model, and second order Sugeno model very rarely is used. So these are Sugeno models of different 0, 1, and 2 degrees, depending on the type of deterministic function, whether constant, linear, or second order deterministic function of the inputs. So it's interesting. I told you that when you have some measurement and satisfaction to a certain degree of the condition, to this same degree we qualify our conclusion. Instead of reading all this, which is the mathematical explanation why we cut the conclusion to this degree or scale the conclusion with the degree of fulfillment of the condition, I will give you an example. Let's first speak about fuzzy logic controllers, and the example is after that. The fuzzy logic controller usually is based on PID, the 3-term. So we need the dynamic part is the called pre-processing, and we need 3 variables, one for error, one for integral of error, and the third for derivative of finite difference, approximation of derivative for the error. So the combination of states increases the number of rules. So imagine E has 3 states, integral has 5 states, derivative has 2 states. So the product will be 3 multiplied by 5 multiplied by 2, 30. 30 rules. So to reduce this, we use PI controller, which is most widely distributed, and its incremental form to eliminate integrator and to be able to perform some normalization of variables and of the universe of discourse. So instead of temperature between 0 and 100, we can have dimensionless variable relative temperature with respect to the range 100. So all measured values are divided by 100, and we'll obtain values for this dimensional temperature between 0 and 1. In incremental control algorithm, we obtain 2 inputs for the PI controller, derivative of error and error, and the number of the combinations is not great. Usually derivative of error has a positive, negative, and norm 0 derivative, while more terms and more fuzzy sets respectively we need for the error. We arrange negative, small, norm, positive, small, positive, great. So the abbreviation has logic, naming one symbol is abbreviation for sign, the second symbol is abbreviation of magnitude. And we arrange from the um, left end of the universe of discourse each adjacent, adding adjacent terms till the rightmost fuzzy set labeled positive grade. In the same manner, we arrange the terms, respectively the fuzzy sets, for the second input. And we have to fill in this table with the conclusions, the action, the control action, which is the derivative or this derivative is usually computed numerically in a digital controller. Delta UK is the finite difference that approximates the derivative. So inside are the states, 5 states, negative great, negative small, norm. So norm means 0 error, 0 derivative, no tendency, no velocity. So this table is filled in with the rules conclusions. Each cell gives one relationship. The first cell shows if error is negative and delta error, if error is negative grade and delta error is negative, then delta U is negative grade. Why? Because grade error means current measurement UK at time moment TK is greater than reference. It should be returned to reference. This means we have to change. New value of error is previous, if this goes to the left, plus the update delta UK. So delta UK should be negative to reduce previous error, previous control action. And reducing the previous control action, we reduce the output of the plant and respectively this output is more close to reference. From this we conclude the sign of our delta UK, the correction. This is the correction of previous control action. It's given here. It is computed on the basis of the error and derivative of error. On derivative of error, which is finite difference of error and error. So, why great? We speak about the derivative. The finite difference for the error, we substitute errors at moment k and k minus 1. The reference is the same, preserved, and we obtain negative delta E, means the new measurement is higher than the previous. There is no tendency of moving towards reference, decreasing of this value. So we need to apply great negative correction of control action from previous time moment. So we reduce the output controller, the output control action by decreasing with negative update delta UK. So in the same manner, we have to fill the conclusions in all rules. So there is some relationship between error, derivative of error, and delta U. The relationship is the null line when the change delta U is 0. For 0 error and derivative of error, this is the null line. Above it, the sign of the correction delta U is negative. Down, this is positive. And when the cells are closer to this switching line with 0 correction, this is a switching between the signs from negative to positive. So close to this line are the medium values, the small ones, the medium, and at the corners we have the greatest values for delta U belonging to the both sides of the universe, normalized universe of this course. Now, because error has positive and negative values like the derivative of error, we have to normalize the universe of this course between -1 and +1, because inputs are not temperature but error. The second input is derivative of error. So their maximal ranges are to be known in order to find the proper gains that will normalize them in the range -1 +1. The same normalization is included for delta U. After we process this table, we'll obtain the fuzzy set for the control action delta U, the qualified conclusion in its rule, and these qualified conclusions for all rules are united. Union is obtained, and the union is the final fuzzy conclusion for delta U. So let's see how it operates. We have two rules graphically described in a Mamdani model using the clipped conclusion. So the qualified conclusion is by cutting part of the conclusion in the rule. The first rule says if measurement, so we need measurement or some realization or estimation of first input. In the case of controller, this is error. normalized error. If normalized error belongs to A1, so if it is A1, and normalized delta error is B1, so the belonging to A1 is 0.6, the belonging to of a derivative to B1 is 0.2. Because I said the first condition is X1 is A1 and X2 is B1, the end requires the two subconditions to be united. So the membership functions 0, 6 and 0, 2 are compared and the minimum taken, the minimum operator for fulfillment of AND operation. And it cuts the conclusion. Then Y is C1. Yes, it will be fully C1 in case we have fully satisfied both subconditions, but they are satisfied to a certain extent, and the conclusion takes the minimum. The same with rule 2. It states if x1 is A2 and x2 is B2, the degree of matching of measurement with fuzzy set is 0.4, for the second is 0.7, the smaller is 0.4, it cuts, then the conclusion is then Y is C2, but taken to level 0.4. So this is the Mamdani rule for fuzzy conclusion of each rule. Then we unite rules. There is another method, Larson implication, scaling rule. This minimum fulfillment of the two subcondition is used to scale the fuzzy set in the conclusion of rule 1. We'll obtain this small triangle. And in rule 2, and unite the qualified conclusions, the scaled triangles. In this case, we apply the prod function for AND, for activation. So the process are called fuzzification when measurements are turned into membership functions to the corresponding fuzzy set in the rule condition or subcondition. Then we have degree of activation of the rule, taking the fulfilling AND or operations, taking the minimum for AND. So this is the activation of the rule, which is actually the degree of fulfillment of the complex condition. So the activation of the rule is related with the way of using minimum, cutting to this minimal value, or scaling, making product of the fuzzy set in the conclusion with the minimum from union intersection of the two fuzzy sets with the measurements. So 0.2 is the scaling coefficient, and the final conclusion, activation with prod, is Larson. And the union is usually with maximum to take the cover, or with some where cross sections exist, they will be taken twice. So better take accumulation using the operator sum, because accumulation is union. Either the sum operator, the maximum operator you need, or the other operator, which is algebraic sum. Two operators for fulfillment of union. So, you have a question in the test related to draw these diagrams and explain how fuzzy logic conclusions are obtained. And after we have this fuzzy conclusion, we cannot apply to control action should have a CRIPS value, which means definite value. We just use some of the methods called defuzzification methods from the fuzzy conclusion to derive single value, CRIPS value, by applying center of gravity method, discrete center of gravity when in the conclusions you have singletons. This is Sugeno model, and you qualify each singleton to the degree of activation of the rule or satisfaction of the condition. So you have qualified singletons from several rules, and you apply this simple formula, which is easy for computing, because defuzzification is a very difficult for computing operation. The best method is this center of gravity, but you see here this is union. This integral stands for union of this product. So we can sum if we discretize and obtain the same discrete center of gravity applied for singletons, and for the others after discretization, you take the sum value on the abscissa multiplied by its degree, its height, the height of the singletons over the sum of, so it's weighted average for discrete values on the abscissa. We can use also method bisector, divides the area of the fuzzy conclusion into two equal areas, or take the maximum. There are several maximums in the middle of the leftmost, the rightmost, and this is easy to compute, but however, in next measurement, when we have disturbance, this maximum may move on the next and the adjacent membership function in some of the conclusions, and the control action will jump from position here to another position, like in a relay control, on-off control. So it is a relay controller using this maximum defuzzification method. We have normalized inputs here between 0 and 1, and we define normalized output through the universe of discourse which are normalized, and when we compute using some software like MATLAB, like fuzzy control of Siemens, we make different discretization on both inputs, take values from, make combinations of all values, and compute using this system the defuzzified output. And the result is a control surface which we can use to train a network, or we can use as a table if the fuzzy if the programmable logic controller has this facility and has no facility to produce fuzzy logic control functional blocks. Usually Siemens has this facility, but most controllers have many facilities and they can have this table. So the real-time fuzzy control is very easy to produce because this table is before computed. It takes no time. The controller has this fuzzy controller part with fuzzification, the rules, aggregation, activation, accumulation, final conclusion, defuzzified, and dynamic part. So this is non-linear static transformation of input into output. And also dynamic part for preparing derivative and normalization, and dynamic part for denormalization of the control action, and integration, because this delta U corresponds to derivative. The integration through actuator, proper induction electrical motor, or sometimes the plant contains integrator in its model. These are the plants without self-regulations, and the plant performs the integrating. Or we can use, instead of integrator, this can be used as correction of previous control action. So we memorize the previous control action and add delta U after denormalization to obtain the new control action. For this purpose, we need rule-based database. This means that we program this fuzzy part using some software. So up to here, then the other part you read by yourself, and we'll go to our laboratory. So here you see different applications. Again, this plant, you use fuzzy logic for modeling with prediction of the output dilution rate in controlling this very slow plant anaerobic digestion of organic waste. So we have different comparisons and a possibility to apply tuning to this fuzzy controller by the help of transforming fuzzy logic model, if-then rules and fuzzy sets, to network-like structure, which from experimental data, training couples PD can be tuned. So it is combining network advantages with fuzzy logic advantages. So I'll stop the lecture up to here. This is our last laboratory using MATLAB, laboratory 3. We'll design Mamdani fuzzy model for a mixing process where we mix hot and cold water to obtain two basic effects to have desired temperature and desired flow rate, strength of the flow. Flow rate is the quantity per unit of time, or the volume of liquid per unit of time. So here there is a theory we studied in the lecture. Fuzzy sets are ordered couples, elements with their degree of belonging, and they can be different. Here MATLAB allows to obtain different fuzzy sets, to assign different fuzzy sets to the states, and with different parameters. So here there is explanation why fuzzy logic is multi-valued logic. The two-valued logic is related with belonging and not belonging to a given fuzzy set, while the multi-valued logic, it belongs but to a given degree. So the basic operations that construct each fuzzy logic are and, or, and not. This is the minimal logical system with which we can express any other logical operation. MATLAB allows us to use fuzzy toolbox, which complies with the requirements of the standard of language and programming of programmable logic controllers. It contains an editor in which we assign the number and the names of the linguistic variables at the input and at the output. So I'll try to make this bigger. And after that, we'll open MATLAB to see this. Besides, we have a membership function editor to select proper shape with proper parameter and to give names, the labels of this, the terms of membership functions. Then we have a rule editor to select which complex conditions and their connective. For instance, first input linguistic value or label of the first and with the second. So the result should be, or the conclusion should be, some linguistic value or term or label related with the conclusion. And all these if-then rules, they embed our experience in driving this process, in controlling this process. The way conclusion is derived, it's derived on the basis of experience implanted in fuzzy sets and fuzzy rules, also based on words, operation with labels, and after the words we know stay these values from the universe of discourse where the fuzzy sets are defined. And in deriving the conclusion, we have similar rules in the way our taking decisions as humans is performed. So we take decisions in the same manner. Here the conclusion is obtained on the basis of degree of fulfillment of the condition. So here the whole rule base, the whole all combinations of states for the inputs define the number of rules, and the conclusions are related with the table of rules, which is called associative matrix, fuzzy associative matrix, because it's applicable for 2 inputs and 1 output. It's a matrix. So after we design our controller, first in the FIS editor, FIS is fuzzy inference system. We assign the basic rules for union, conjunction, for intersection, union, for accumulation of aggregation of how we perform and or. This is aggregation of subconditions, and accumulation of individual rules, fuzzy conclusions. This accumulation can be with the sum and or with the maximum. So we have to define here and the defuzzification method. But before all, we start with selection what type of model we want, Mamdani or Sugeno. And when we have all that arranged, don't forget that when we start with membership functions, their number, allocation, type, we have to define the universe of the discourse. It is normalized. And the normalization gains are usually tuning parameters of our controller. Normalization at the input and denormalization at the output, they can be tuned because they are based on the maximal range of changes of error, derivative of error for controller, or the two inputs, and the output is fixed -1 +1 if it takes positive and negative values. So after we have the model, we can simulate. First, we'll see the using surface viewer. This is the same with the fuzzy control in Siemens. Only the limitations are the maximum number of rules, the types of membership functions at input trapezoidal and sigmoid and singletons at the output. So else all these stages are related with the standard for programming, and they are available in each software related to some type of programmable logic controller. So we see the surface, and we can have different scales, discretization, to make it smoother, and we can have graphical representation of rules. What I showed you how the controller operates in deriving fuzzy conclusions through measurement. The red lines are the measured values, and you can move them, and you see here only the middle term is totally active in yellow for the first input. The second output has in the middle some value. It's not easily here to distinguish. And the result is totally activated rule 2. So rule 1, 2, and 3. And this is the only, it is not in union with other conclusions. And this result further should be defuzzified, applying the method you have chosen from the first window in this fuzzy inference system. So, the Gaussian Bell type sigmoidal, like in neural networks, functions and other membership functions are in the library of MATLAB. And what we have, temperature and flow, two variables we control by the taps for cold and hot water. So membership functions and labels for temperature and for flow should be inputted in the MATLAB fuzzy toolbox to obtain this allocation describing the states for temperature. So the range is not normalized for the two inputs. It should be the absolute range should be given in the window for the membership functions, in the editor for membership functions, and these are the parameters. So 0, 0 for trapezoidal membership function, this is the type, and 4 parameters where we put 1.5. So first point is this one, second is equal to this one, 0. It is the project of the small side on the top of the trapezoidal figure. The projection of this end of small side is 105, and the fourth parameter is 3. So all projected peaks are denoting the parameters of the corresponding membership function. So we have to obtain the flow and two different outputs, valve hot for hot water and valve cold, which has the same relationship. The rules are experimentally by experience obtained. So if temperature is cold and flow is small, then the valve for cold is open slowly, while the valve for hot is open fast, which means to a great extent. So a little cold water and much more hot water to increase flow and temperature. So if temperature is cold and flow is middle, next state for the second, and another combination of the two inputs. So the flow is middle, which shows valve cold will be closed a little slow, while valve hot will open slow to a smaller extent, so that the flow should not become great. We have to decrease by decreasing cold water to decrease the flow rate, the strength of water. It's good for bathing, for instance. And at the same time, the decreasing of cold water leads to decreasing of flow to its norm, while the valve hot is increasing the temperature. So it influences the flow, but it is compensated by closing valve cold. And after experiencing, we have several such combinations. The total number of rules is 9. Миленчов, час съм, ще ти звънна по-късно. Sorry for the interruption. So the rules should be entered. This is the table, fuzzy associative memory, because each output is associated with the input in the condition, and it should provide proper action to move the input to its norm. So if the flow is small, middle, great, and temperature cold, good, hot, once you say this for the position of valve cold, and the hot is fast. Let's see if this is small and temperature is cold. Temperature is cold and flow is small. The tap for cold water is open slow. For hot water is open fast. So for cold water we have open slow. For hot, open fast. The two conclusions are two different output variables which are united. They should take place simultaneously. They are united by AND. Both should take place at one and the same time. So now I will open MATLAB to see how this is applied. Have you got MATLAB with you? At least some of you. At least one. So the answer is no. So you'll be waiting for me to have this model. I have it already from other students, but I'll show you how it operates. Can you see MATLAB? Please give me a sign. Yes, okay. So
Yes, we can
uh,
see that.
I will go to another directory if possible. Um, no, it's not user. It should be desktop, but Okay, I'll close this MATLAB and open my file to enter the proper directory. This file cannot be run, but someone else. When it's Simulink, it has extension MDL or some other extension depending on the MATLAB release, while the fuzzy inference system is related with another extension of the models. They are not simulated. They can be used as blocks in MATLAB, fuzzy logic controller block. When we tell the name of the model, created in fuzzy toolbox, this block, fuzzy logic controller in Simulink, will perform fuzzy logic controller, reading the model with a name. So now I'll try to enter. This is FIS extension for. So in order to reach fuzzy logic toolbox, in the command window where two arrows appear, you type fuzzy. So there is a possibility to read a ready model, importing from file, and I entered my directory with this prepared beforehand file, which corresponds to our problem. So temperature has three states named cold, good, and hot. I'll show you the manual in the same time, but I have to reduce it. So these are the membership functions for cold, good, and hot in the range. So first assign the range 0 and 60. Then you define what type from here is each membership function, how many they should be. So first we have to define the number of inputs and outputs, edit, and I will demonstrate using a new file in parallel. The new file is untitled. So this is open when we start from the beginning. Input 1, output 1. We select input 1 and add input variable. Then we select output and add new output variable. Do you see well?
Yes, we can see.
Then you select first input and give the name call, or the first input is temperature. Probably with small letters. It's not necessary. So it's temperature, and the second is flow. And the first output is related with valve hot, valve cold, but this dash is not possible. So valve, let's see if maybe it's possible, but I wrote somewhere on the screen. Valve hot. The first is valve hot or valve cold. Let me see my file. Valve cold is the first, so valve cold. The next is valve hot. These are the two tabs to control flow rate of hot and cold water. So I select end method minimum or method if necessary. Here it's not necessary, but it's maximum. Implication min, which means Mamdani. Aggregation through max. This is union through maximal membership. Centroid is center of gravity. You can select from bisector, middle of maximum, leftmost, and so on. Small and large of maximums. So the Mamdani model, we can choose it from the beginning, from here. New FIS, and you choose whether Mamdani or Sogena. Mamdani is it is selected when you do not make any other changes. So when you enter temperature, you change the membership functions. The membership functions you use edit, remove all, and edit, add membership functions. You say 3 triangles, okay, but these should be changed into trapezoidal. And I have to correct the parameters. This trapezoidal, which has the name cold. First, I'll name it with label cold. In the middle is good. And the highest is hot. I see from manual. Then the parameters I'll give the first 0, 0. The range. The range is from 0 to 60. It's very important because you'll see how they will change. Now, from 0 to 60, the first has parameters, so I have to select, and in the brackets to change the parameters. 0, 0, because it is trapezoidal with right angle. Then 15 and 60. I look at the manual for the parameters. Oh, cold, 16. No, I don't think 16 is 30. It's mistake in the manual. So the last is 30. This in the middle, it should start from 15 because 1 from cold starts decreasing. So from 0, from this position, 15, the next will start increasing. 15, the middle is 60, and the final is 45. 45, because it's given here in the manual. So the next will start at 30. And the top is the first part of the small side of the trapezoidal figure should be at 45, because the sum membership functions should be 1 for orthogonality, and the two coincide because of a right angle. So I have this. We do the same with the flow. I'll quickly change from 0 to 6, first the range. Then I delete all. I may not delete, there are 3. Only these are changed into trapezoidal. And then I'll give names. The first is small. The name is, or the label is important. The next is middle. Middle flow is our norm. And the last is great. Now the parameters of the first. We set 2 zeros, so inside. Don't forget brackets are necessary. 0, 0, then 1.5 till 3. I'm looking the parameters given here. In the middle will be on 3, but the beginning will be 1.5 to start increasing when the other is decreasing. The previous is decreasing membership function, and the final is 4.5. And this will start at 3. Then 4.5 and so we need similar entering valve cold and valve hot. What happens? Someone is asking questions. So do you have any question by now? So imagine you need here the scale, and 2 times you will repeat for valve cold these membership functions, and for valve hot the same, but the same membership functions with the same labels. And now I'm not losing time. I'll show you what is introduced in the ready file. The ready file, we have this tool, which I showed you how performed, and close fast, close slow, steady, open slow, open fast for valve cold. The valve hot has the same, only small change. Why? This is 9 07 09, maybe I moved it somehow, 07 to be more precise, 11. So we have this correctly and this correctly. So when we have all membership functions, we use to introduce rules. So to introduce yours, you select the first input state code or label code, and one after the other, 4 rules will select the second input. So code is repeated 3 times with different flow, small, middle, great. For each combination, cold and small, You select here open slow for cold valve and open fast for hot valve, following this given rule. Valve cold open slow, valve hot open fast. So valve hot is open fast. Open fast is the last trapezoidal membership functions on the right, the highest values. So the range is important. I didn't give you, but from 0 to 1, 1 is fully open, 0 is fully closed. And if you need to, you select end connection between the two inputs in the two sub conditions. And you continue selecting, so code with 3 times of flow, different conclusions for the first output, the second output, then temperature is good, and again 3 times it's good, good, good. The other is changing to make all combinations and the corresponding 2 outputs. And the last state for temperature cold, we also have temperature hot. We also have 3 second variable states, small, middle, great, with the corresponding. If we are mistaken, we can delete some rule, or we can add additional combination, missing combinations. So we can use even not hot is another state which will give the sum hot, not hot. Not hot is another fuzzy set which has membership function 1 minus the membership function for hot. So it is complementing hot. If it is triangle, hot is trapezoidal. All the rest from here increasing till here and staying 1 to the rest is not hot. Sorry, for hot we have to speak. This is for temperature. So this is hot, but not hot is defining its complement, starting from here, increasing to 1 and staying for the rest of the universal discourse to 1, because hot from 30 to 0 has value 0. So the complement to 1 is that the not hot should have value 1 in this range. So these are the rules, and you have everything, and I'll close rules and we'll go to simulating. Untitled is what I showed you how it operates, but view rules, we can see whether we have correctly obtained all combinations. So this is changed, the second membership functions change, covering all states one after the other. First, next, and the third. First, next, the third. First, next, the third, while preserving the first at one state. So 3 times state 1 for temperature. We enumerate the 3 states for the flow. Then the second state of temperature, fixed 3 times to enumerate the 3 states for flow. This is how we obtain all 9 combinations of the states of the 2 inputs. And we have, this is operators' experience in the rules. So we have them properly. And this red line is we measure temperature. we can assign temperature and flow by values or move these red vertical lines. These vertical lines cross in different rules the corresponding state defined by fuzzy set. The yellow, they are active. They have membership functions, measurement corresponds to this state, to this degree. So the cross point is not at 0, but at some degree different from 0. In the yellow, you see the level of matching of measurement with defined in the corresponding rule. So the number of the rules 1 to 9 matches the corresponding fuzzy set to this degree. The second input, which is flow, also activates these subconditions in yellow to the corresponding degree, where we have active both subconditions with degree of membership different than 0. So here we have conclusion active. This is degree of activation of rule. Because the union is AND, both should have non-zero membership function, and we take the small one using Mamdani inference to cut the conclusion to this level. Then you see here very high level, the smaller one is the one to cut the conclusion in the first output, in the second output. Option, no, we can view surface also. To view surface, this is the discretization for X and Y, for temperature and flow, and output valve code. For output valve hot, it's different. You can rotate to see better. Also, you can, with the right button, go to some projection. Projection, temperature, how influences Z, the valve selected. So this is how we obtain relationship temperature valve hot. And all these lines fix one constant value for the second input flow. So if we take the same for valve code, it will look like this. Then we can have original valve code rotated to see that it's non-linear. So this is how we manually control to have good temperature for bathing from the shower and good flow, because if the flow is too hard, it's painful. And when it's too slow, we cannot bathe normally. At the same time, the temperature should be kept in some range, some fuzzy desired value. Temperature is good in this range. The best is 30 degrees. So, any questions now? I'll stop the recording.